questions for a chance to get them answered on my next live show. So we had some technical difficulties, and this actually wasn't live. Unfortunately, it just wasn't working. It started off with a live stream, then it was choppy, and at least what I can do is record my lesson and everything that I was going to go over, because I did answer several questions and I know you guys have tests coming up. So for just in case you guys are new to these lives, they typically are live. And what you can do to get your question answered if we're not covering that today is you can tweet me your questions at Hello Melissa M and use the hashtag AskMelissaMaribel, and make sure to tweet me ahead of time. So earlier in the week is better, because I start writing my lesson on Saturdays. So at Friday night at the very latest, make sure to tweet me your question. And everything that I'm going to be going over today is literally worth $100 worth of tutoring. Actually, I'd say more, because we're going to cover a lot of different things today. And it's going to be a little bit of general chemistry 1 and 2, all kind of mixed together. And something else that I wanted to mention is just all the different topics that I'm going over. They're going to have different formulas, different tables, and just nice little helpful tables or diagrams that I have already made for you guys. You can find that all in the description box. All of my resources are going to be in the description box of this video, and they're really actually in every single one of my videos. Make sure to download your free chemistry survival guide. That's where you're going to find all of these formulas that I will be covering today. Another thing is, if we're not covering what you need help with right now, then I highly recommend checking out other resources. Like if you need homework help, this was a lifesaver when it came to helping me out in college. When I was actually a chemistry major, if you guys didn't know, I took a lot of physics classes, math classes, chemistry, biology, so much. And I always had questions on my homework. So Chegg Study was something that I actually used, and it was a lifesaver. It was a lot easier to understand all of my homework, because they literally had the step-by-step solution. So if you need some help with that, make sure to check the description box. All of the links are going to be there. And just as a little disclaimer, I am part of their affiliate program. So if you do decide to go with Chegg Study and purchase Chegg Study, then I do get a small commission that just goes to making more videos for you guys. Okay, so let's jump right in. This was a question that a student actually tweeted, and there was actually 2 different students that tweeted to talk about Gibbs free energy, entropy, and spontaneity. So let's go over that. That's going to be the first thing that we're going to dive right into. So before we get into all of these, main topics with Gibbs free energy, and this is really thermodynamics, let's go over what all of these are really talking about and what they all kind of mean. So even before going into Gibbs free energy, if we were to just look at, let's say, entropy. Entropy is represented as an S. So we have entropy and enthalpy. So beware of those two. They are a little bit similar in how they sound, but enthalpy is represented as an H. So remember, enthalpy, that H, is actually referring to the heat being transferred. So it's heat transfer, whether the heat is being absorbed or released. Now for entropy, this is talking about the order of the substance or whatever we're observing. So let's say for entropy, what I want you to think of is it's kind of like chaos. So it's kind of like disorder. So if we were to have a solid versus a liquid, and we were looking at the actual particles or the molecules that are within that structure, which one would be able to move more freely or essentially be more chaotic? So the liquid would be able to do so, because a solid is ordered, it's intact. We can't really do much with it, right? You can't really make it move as much as a liquid can. So, or even like a gas would be it would have the most entropy, because it would be the most chaotic, because it's literally able to kind of go everywhere, right? So that's the concept with entropy. When entropy is positive, that means it is chaotic. There is entropy there. If entropy is negative, then that means there is no entropy and it's ordered. There is no disorder or chaos. Okay. So before I jump back to Gibbs free energy, why don't we just dive right into entropy? So all of these formulas that you're seeing on the screen, make sure to know. So especially these 3, okay? Especially note these three, I often see these on different test questions or even homework problems. So the first one is going to be talking about the entropy of the universe, and that's going to equal the entropy of our system and the entropy of our surroundings. Now, why do we do this? Why do we care about the entropy of the universe, and how is that relating to the system, the surroundings? What does this all mean? So if you're not sure what this all means, let's give you an example. So let's say you're the system, okay? So you're the system, you are what we're analyzing or observing, and your surroundings are wherever you're located at, all right? So maybe you're in your home, or maybe you're just in your city. So those are your surroundings. Now, what if we were to kick it up a notch here, and what if a zombie apocalypse were to just break out? Because that happens, right? So what if that were to occur? Well, that would be more chaotic and there would be more disorder, right? Everyone would be going crazy. So you yourself would experience more chaos, as well as your surroundings are also increasing in how chaotic it can be. So then the entropy of the universe entirely, because it's the chaos that you have and the chaos that you're surrounded by, that would mean that the entropy of our universe is chaotic, right? That's why we're adding those two together, and that's why they relate to each other. So that's kind of explains this first formula. Next, we could also relate the entropy of the universe as talking about our temperature and our enthalpy. So note that we really just kind of changed this entropy of our surroundings, and we replaced it with a negative delta H divided by our temperature. So that's something to definitely note. We could also state that the enthalpy, change in enthalpy, is also equal to the negative heat of our surroundings. So these are just formulas that I highly recommend you understand and know. And then lastly, this one we're going to see quite often. Something to also note is this little degree symbol and what that means. So anytime you see this little degree symbol, all that's talking about is that it's under standard conditions. So whatever, like our reaction, our solution, whatever we're looking at, it is under standard conditions. All that means is that our temperature is at 298 Kelvin or 25 degrees Celsius, and our pressure is 1 atmosphere. So you're going to notice that here, right? This 298 just means it's at under standard conditions, and our temperature is at 298 Kelvin. So this formula is going to be really important because this is specifically going to help us understand the system, so the entropy of our system under standard conditions. Okay, so let's go back real quick and explain a little bit more on Gibbs free energy. So Gibbs free energy is going to help us figure out, is this reaction spontaneous? Is it non-spontaneous? And how our entropy and our enthalpy and temperature all come together to help us understand if the reaction is spontaneous or non-spontaneous. So what is spontaneous? What is non-spontaneous? Like, what does that even mean? Well, think of it this way. For a reaction to be spontaneous, essentially what we're trying to say is that our reactants will then go to our products. So our reaction will completely go through or occur on its own without us having to add anything additionally like a catalyst or increasing its temperature. All right, so that's what we're talking about when we're talking about spontaneity. A spontaneous reaction will not need any additional help to actually get to complete the reaction, to get to the products. However, a non-spontaneous reaction will need that help. So a non-spontaneous reaction doesn't just kind of randomly go from its reactants to the products. It needs a little push, all right? And that push, once again, could be increasing in temperature or a catalyst. So that's what we're talking about, and that's what we're really looking for with our Gibbs free energy and seeing how everything is going to relate. So let's put this all together and let's jump right in. And then we're going to go over this table a little bit later to answer one of the questions. But what you're going to see is this table is extremely important because there are four main cases that you will see in, thermodynamics, showing you, okay, what happens when our enthalpy is negative. So that means our heat is being released. And then what if we do have entropy, right? It's positive. Well, at either doesn't matter the temperature, low or high temperature, we will have a spontaneous reaction. So all of these are going to come into play when we're asked a question and saying, okay, well, we figured out our enthalpy, our entropy, and our Gibbs free energy. Will it be spontaneous or will it be non-spontaneous? And that's what we're going to find out. Okay. So this is a common test question or a common worksheet that I've seen before. So what they would do is they would give you the actual balance equation and they have to provide you with the values, okay, to figure this specific one out. So let's just start off with part A. And just a little thing here is part A, B, and D are very, very similar. It's pretty much the same exact formula, which we'll go over. Okay. So this is saying to determine our change in enthalpy under standard conditions, because that's what this little degree symbol means. Plus it's telling us that it's at 298 Kelvin, which is under standard conditions. So the formula that we're going to be seeing here is this one, where all of this means, remember that our N just refers to our moles that we have in our balance equation. And then next, this is telling us the change in enthalpy of our products, which we're given. And same thing goes for our reactants. We're just going to subtract those two. So let's just put this all together. And I'm just going to separate this. So all I did was I said that, here, let's go over this. There we go. So all I did was this is going to be our reactants. So that has to be on the right side. And then our products has to be on the left. And remember, this summation notation is just telling us that we have to add all of our products together. And if we had multiple reactants, we would also add those together. So in this case, we only have 2 products. So then that's why I only placed the mercury and the oxygen gas. And then from there, this is also talking about our N, or our amount of moles. So here, 2 would then be coming from our balance equation because there was 2 here. And then 1 here because there's really a coefficient of 1 right here. And then next we'll subtract that by our change in enthalpy for our reactants, which is, this is just our only reactant, and we have that 2 in front. All I'm going to do is plug in all of the values that we are given in our table. So be aware, sometimes they give you additional information, and that's kind of meant to trick you, unfortunately, where your state does absolutely matter. This is a liquid, not a gas, so don't choose this one. Choose 0 instead because mercury is in its liquid state. So I'm just going to plug everything in, and then we'll do the math. So this would really just, this part would just go to 0, right? 2 times 0 is 0, plus 1 times 0, 0. And then we'll just multiply everything here, and we will get a positive value. So that's the first answer. That's the first part of just finding our enthalpy change for this reaction so far. Let's keep going. Okay, we're going to come back to a lot of these different formulas to then kind of see, is this spontaneous or non-spontaneous? Okay, so now determining our change in entropy for the system. So for the system, it's pretty much the same exact formula. But only difference is really that it's entropy instead of enthalpy now. So remember, entropy just means it's S. Enthalpy means it's H. Okay. All right. So all I'm going to do is really the same exact thing, where all I'm doing is changing my values, because now we have different values. And just note that our entropy units are joules per moles Kelvin versus enthalpy is kilojoules per mole, and Gibbs free energy is also kilojoules per mole. So I'm just going to plug in the values from the given table. So all of these values I'm literally just plugging in, and then always make sure that we're plugging in the right one. So that's what we have so far. I'm going to add these 2 together and subtract by these 2 multiplied. And this is what I would get for my system, for my entropy of my system under standard conditions. So good so far. Now let's keep going. So this is really just the same formula and understanding how to use it. All right, this is where it changes. Because this is asking for the entropy of the universe, we're not going to use the same formula. Instead, there was a specific formula for that. It was this one. So we have enough information because we just found that in parts A and B. And in part A, actually, we found the change of our enthalpy, and in part B, we found the change of our entropy of the system. And then we know the temperature, since that's given as 298 Kelvin. So all of these are given. Could we just plug in? No, because all of our units are not the same. So just always make sure that this is actually in the correct unit because this is joules and this is kilojoules. So I'm just going to convert the kilojoules to joules and then I'll plug it all into the same formula. So then we'll convert this to kilojoules by multiplying by 1,000. And then our kilojoules and kilojoules would cancel. And then next we'll be left with joules per mole. So that's what we would have. Now I'm going to plug it in to the formula. Okay. So plugging everything into the formula that we previously found, once we do that, that would give us the entropy of the universe, which is negative. Okay, let's keep going. So far it's just understanding how to use those formulas and when to use those formulas. So part D is very similar to part A and part B, where it's pretty much the same formula, right? The products minus the reactants. So still going to use the same exact setup. Instead, the only difference here is that we're going to have different values from our given table. So I'll just plug everything in. This is going to be 0. There we go. So is this other portion, and then this is going to be that negative 58.5. Multiply everything out, add them together, and this is what we get for our Gibbs free energy. Okay, so far, really just plugging it into formulas. The last step is going to relate everything together. So this is saying, are the results in parts C and D consistent? Explain using spontaneity. So what we're looking for is we're really looking at a table, and we'll cover that. But first, in part C, what we found our entropy of our universe, which was this, and it was negative, right? So it was negative, meaning it's less than 0. So anything less than 0 means it's negative. And note, what does that mean when we're talking about entropy or chaos or disorder? Well, entropy, when it's negative, means it's not there. It's not present. So, okay, then I know there's not really much chaos in the universe. It's a calm day. So now we'll see, how does that relate to Gibbs free energy? And is this a non-spontaneous or spontaneous reaction? So we found in part C, I believe, that this is our Gibbs free energy. And we said, okay, our Gibbs free energy is positive. So meaning it's greater than 0. All right. And we'll understand kind of what is that talking about when it comes to spontaneity. Well, this table comes back into play. And this is going to be very, very important to know. So let's identify and kind of use this table to see what this all means. Okay, so I really put yes, but we'll explain what that means. So our entropy of our universe is negative, right? So I'm going to go here and see, okay, well, this is when it's negative. And then we're seeing, well, I wouldn't say we're changing the temperature, right? It's under standard conditions. 298 Kelvin is room temperature. So it's neither low nor high. But here we have our Gibbs free energy is positive, or it's greater than 0. Well, I can see that here, right? That both of these are telling me, well, this is non-spontaneous, this is non-spontaneous, and even here, this would tell me the same thing, where all of these are non-spontaneous. So if it asked you what type of spontaneity is this, is it non-spontaneous or spontaneous? It's non-spontaneous. And that's kind of something to definitely help us understand, does this work out? The reason why it's a yes on the consistent end is just the fact that it actually goes hand in hand with the table, and it actually makes sense when we're relating everything together. So if it's going hand in hand with this table, that means yes, it is going to be consistent because it's a non-spontaneous reaction. So understanding how everything kind of interconnects and goes together is going to be very, very important. So definitely know this table. And once again, all of these resources, the tables, the formulas are going to be found in the description box. So make sure to check that out. This is my free chemistry survival guide. It has both chemistry 1 and chemistry 2 formulas and different tables that I recommend. All right, so let's keep going to our next topic. And this is on thermochemistry. So this is now going back to our general chemistry part, actually 1. And this is going to be a more advanced question. So I can see this being either an extra credit question, or you might have a challenging professor, unfortunately. But it is connecting a lot of different types of concepts of thermochemistry and putting them all together. So let's just read this, and then we'll build a plan, and we'll go from there. Okay, so let's put this all together. So this question asks, or says, you will boil water to drink. You plan to use 35 liters of water. How many liters of fuel, and it gives us our fuel, do you need to bring? Assume that only 15% of the heat generated from the combustion of the fuel goes to the water. Also assume that the density of the fuel is this, the initial temperature of the water is 25 degrees Celsius, and that our change in enthalpy of formation is given. Okay, so they give us a lot, but we know that we're going to try to figure out how many liters of fuel we need to bring. But there's a little hint here, and this kind of tells us that there's a lot to this question, is the fact that it's saying assume that only 15% of the heat generated from combustion of the fuel goes to the water. So that's going to be talking more about, if we recall, talking about thermochemistry when we're looking at the heat of our system and what that's equal to the heat of our surroundings, remembering that those are opposite signs, that the heat of our system is equal to the negative heat of our surroundings and vice versa. Just knowing that they have opposite signs is going to be extremely important. So that means we're going to have to figure out two different types of heat and a lot more. So what I would do first is just build the formula. That's something that we're absolutely going to need throughout this question. And how I built this, how I just instantly know what type of reaction it is one, they gave me what the fuel was, right? That's just some sort of hydrocarbon. Hydrocarbon meaning it's consistent. It consists of hydrogen and carbon. So that's what I have here. And then next, it is telling me it's combustion. It's a combustion reaction, and combustion reactions always have oxygen gas in on our reactant side, and then they both produce carbon dioxide and water. And then we just balance this out. So that's how I know that this is what it would actually be for our balanced equation. So going from there, let's just talk about all the different types of pretty much the plan that we're going to be looking at here. And then even before doing that, just want to mention also that I do have new thermochemistry notes that pretty much have all of these topics there. So they have a bunch of different examples and practice problems all laid out. It's literally 50 pages worth. So I worked really hard on that to just make sure to simplify it down, because I know how complicated your textbooks can be. It seems like they're written more for a chemist rather than a chemistry student. So I made sure to write for a chemistry student. So that's what you can find in the description box. All the links are going to be there. So our first plan, our first step here, is to calculate our change in enthalpy of the reaction, okay, under standard conditions. So that's what this is telling us. That's what we're going to do first, and that's actually why they give us our change in enthalpy of formation of this hydrocarbon, or heptane. So in this case, after that, I'm going to actually find the heat that's required for the 35 liters of water that was initially given. From there, I'm going to find the heat generated. So it says it's 15% of the heat generated. That's what I'm going to figure out. And then next, I'm going to find out, okay, what are the moles of this needed, of heptane needed? And lastly, I'm going to find the volume. So finding the liters, that's what the question's actually asking. So let's go. Let's start this. Okay, so calculating our change in enthalpy of our reaction, we've pretty much seen this already, right? It's the same formula again, where it's going to be the enthalpy of formation of our products minus the sum of our enthalpy of our change of our reactants. So they should have provided you with a formula, a different chart. So they have to give you all of these values. There's no way to move further, or there's no way to just figure it out or memorize it. So make sure that they do provide you with that if this is on the test. And if the professor forgets, just raise your hand and ask. Sometimes they forget to provide that. So this is going to be given, and all I'm going to do is plug this in to my formula. So rewriting this, we know that let's go back. There we go. That's what I was looking for. Okay, so rewriting this, we know that the N is just talking about the moles in front of each one of these molecules. So next, what I'm going to do is just plug everything in. So we're going to have our products, right? Our products, that's why we have CO2 and the 7 in front, plus, that's what this summation means. We're going to have our water with an 8 in front, And then next, minus the reactants. So these are our reactants. There is really a 1 coefficient in front, and that's what I place here, plus the 11 O2s. What I'm going to do now is just plug in the values that are provided. So I plugged everything in, and then what I'm going to do is just do the math from there. Okay, so multiply, add, and that's going to give us our enthalpy change of our reaction. So that's what we get so far in kilojoules. Okay, so step 1 complete. Next, find the heat required for 35 liters. Okay, so remember that they actually gave us, no, they didn't give us the density, but they did tell us that it's water. And then it is known that the density of water is 1.0 grams per milliliter. In the case that they don't give you that, because they typically don't, memorize it. Definitely know the density of water. I have used this so many times, and a lot of times professors unfortunately don't provide that because to them it's common knowledge. Okay, so they expect you to know it. So next, what I'm going to do is, because I'm given liters, I'm going to use the density of water to then figure out the grams. So, okay, well, I'm first going to look at just finding the grams. And the reason why I'm doing this is because, remember, the heat is talking more about calorimetry, where its Q is equal to MCAT, right? And M is the mass. So we need the mass first before we plug that into the formula. So I'll do that. I'm going to start off with the 35 liters. Then I'm going to convert that to milliliters using 1,000 milliliters. From there, I'll use the density because our liters and liters will cancel. Here we go. Sorry about that. Okay. Our liters and liters will cancel, and then I'm going to try to cancel them out. Perfect. Those will cancel. And then from here, our milliliters and milliliters will also cancel because of the density of water. And now we have grams, which is what we're looking for. So when we do that, that gives us 35,000 grams of water. Next step is to actually plug that into our Q equals MCAT formula. And then from here, I'm just going to highlight what they actually already give you. So we need the change in temperature, right? So we need the change in temperature because that's part of our formula, that Q equals MCAT formula. And we need to figure out what's our temperature, like what's our initial temperature, what's our final temperature. The fact that, well, one, this gives us our initial temperature, right? It literally says the initial temperature is 25 degrees Celsius. But they don't give you the final temperature. And it actually is a hint here where it tells you where we have to boil water. It's also known that boiling water is 100 degrees Celsius. So that's something else to know, right? So boiling water, when we boil it, it is 100 degrees Celsius. So that's going to be our final temperature. And that's what we find here. So our initial, our final, I'm going to subtract final minus the initial temperature, and that will give us 75 degrees Celsius. So now that I have that, let's plug that into our formula, that Q equals MCAT formula. And then we also know that our specific heat capacity of water is that 4.184 joules per gram Celsius. So I'm just going to plug everything in. We previously found our mass, plugging everything into the formula, multiply, and we'll get this amount of joules for our heat. Okay, so that's how much heat is required or needed for the 35 liters of water. Now, the next step is to find the heat that's generated. So we found this previously in part 2. And then something to kind of know is what this was talking about, because it says, assume that 15% of the heat generated from the combustion of the fuel goes to the water. The fact that it says the fuel goes to the water is telling you that it's going to go from a positive to a negative. Okay, so that's your hint here, and that's kind of what I'm showing with this, where the heat of our system is then going to our surroundings, right? The heat of our fuel is our system going to our water, which is our surroundings, right? So that is why we're going to have to change this to be a negative. And then I'm going to go from there. So now that I know that that's really what the heat is technically generated before I take 15% of it, the 15% of Q that we just found that's negative really is talking about 15% of something. So we're going to multiply 0.15 because that's what it would be when it's not in its percent form. We want to change that to a decimal. So we just divide by 100. And then we'll multiply that by Q because of in math just means multiply. And then we'll multiply, and that'll give us our joules. Okay. Our joules that we had previously. Okay, and it's negative. Next step is to find the moles of our heptane needed. So we have our joules, that's the heat that is generated. And what I'm going to do is I'm going to use our, actually first before I do that, I'm going to change this to kilojoules. The reason why I'm changing this to kilojoules is because we initially found in part, actually the first part, we found the change of our enthalpy of our reaction, which is going to be used as a conversion factor because this is now thermochemical equations, also known as enthalpy stoichiometry. So I'm going to multiply this by that enthalpy change of our reaction that we found in the very beginning. So all I'm doing is I'm actually technically dividing that because it's kilojoules and kilojoules. I want those to cancel. Where I'm taking that 1 mole is just from the balance equation since that's here. From there, joules cancel, kilojoules cancel, and then we're left with moles, this amount of moles to be exact. And I keep going. Okay, next step is to find the volume finally. So what I'm going to do, because I just found the moles, now this is saying assume that the density is 0.78 grams. Well, I know I can go from the moles that I just found to then potentially the grams using the molar mass of this molecule, so heptane. And then now the moles cancel. And what I can do now that I'm at grams, I'll use the density as my conversion factor to get to milliliters. And I'll do that actually in the next step. So this is at least the grams. So I'm going to start there. So I'm started off with the grams. Now I'm going to multiply. Now I'm going to multiply by the density. So I'm going to flip that around just because I want the grams and grams to cancel. And then next, I'll convert this to liters by dividing by 1,000. When we do this, we get 2.10 liters, and that's finally our answer. All right, so this is a more advanced thermochemistry question. It's really going to be more for a college level class or an extra credit question, or it's a professor really trying to test you and test your knowledge. All right, so that's how we would approach this question. All right, let's keep going to relating percent composition and how to actually find the molecular formula when we are given some sort of question. All right, so remembering what mass percent is. This is going to be the formula that we're going to mainly use today, with our mass percent being of that specific compound, all right? So the mass percent of some sort of compound that will either be provided, and then from here on top, we'll have the mass of our element, okay? So this is the mass percent, this is the mass percent of the element or whatever we're looking for. And then this is going to be the mass of our element that we had, and then the mass of our compound. So that also should be provided. So we'll see what's going to be given actually. And then from there, I'll multiply that by 100. So let's just jump right in. Let's see what we have for our question. So this compound has a molar mass of this amount and a percent composition. And by the way, if this is a molar mass, this has to be technically by moles. Okay, and it has a percent composition by mass of this amount of X, this amount of Y, and this amount of Z. What is the formula of the compound? So just to kind of note, this X, Y, and Z, they're kind of like placeholders. So we don't have X or Z on the periodic table. Those aren't elements. So I know that I'm actually trying to figure out what elements X, Y, and Z are. So in this case, the goal right now is to pretty much find the molar mass of X, Y, and Z. The reason why is because once we find the molar mass of each one of these, that will help us identify on the periodic table to see what element it actually is. So that's the goal here. What I'm going to start off with is using this formula. They gave us the mass percent of X, and then we don't necessarily know the mass of X in the compound. That's what we're trying to find. And then we do have the total mass of the compound that's also provided. Multiply that by 100, and we're going to do this for every single one of these, Y and Z as well, because they gave us X, Y, and Z, the mass percent of each. So I'm going to plug it in. I'm going to plug in everything that we know. We know the mass percent of X is this. We know the total, actually, we know that for every single one, right? We know the mass percent of Y and Z. Next, we know the total mass of the compound. So I'll plug that in as well. And this is what we have so far. So we're going to do some math to just try to figure out what the mass of each X, Y, and Z is within the compound. Okay, so from here, what I'm going to do first is divide by 100 to each side. So each one of these is going to be divided by 100 just to get rid of that 100 and that percentage. So from there, what will happen is we'll get this value, right? So dividing by 100 really just moves the decimal place 2 to the left. So now I'll do that for every single one. And the next step. So now that we're here, we want to get rid of the denominator. So I'll multiply both sides by our denominator. And when I do that, I get this value. And I'll do this for every single one, just trying to get rid of that denominator. And then now we have the mass of each. However, this is not the molar mass. This is actually the entire mass of however many x's we have in this compound. So we have 2. And then here, our y, we have 3, and z, we have 9 because we've multiplied that. So this isn't the individual masses, it's actually how much in total we have of that x in the compound, y of the compound, and z of the compound. So what I have to do now is to actually divide everything by the moles. And what we're going to do, let's make this a little bit larger. So what we're going to do is we're just going to see, well, x has how many moles? That subscript is going to tell us how many. So there are 2, so I'm going to place a 2 there, and I'm actually dividing by 2 for that. And we'll get this amount for our molar mass. And then next, for our y, this is actually like you're distributing this 3. And then we'd multiply this. By the way, for the 3 and the 3, that would give us a 9. So you're going to see that for the y, it'll be 3, and for the z, it would be 9. And then when we actually divide, this is how much our molar mass of our compound of actually, for our x and our y and our z is going to be. So this is going to be a lot cleaner. There we go. So for our molar mass of each, this is what we have. Now we would look at the periodic table and see which elements have this same exact molar mass or relatively close. So for X, we're going to see that it's going to be aluminum. And this is just what it looks like on the periodic table. So for X, it's going to be aluminum. So what I'm going to do is looking at our formula, because they're asking for the formula of the compound, I'm going to replace X with aluminum since I now know that it's that. So, okay, I replace that. Next, our Y is silicon because it has the same exact molar mass. So I'll replace Y with silicon. And then next, our Z is going to be oxygen. And I'll replace that with oxygen. So that is the overall formula of this compound. So that's what you would do when you're given mass percent and you're asked to find the overall formula of it. Okay. And now on to Bohr's atomic model for isotopes. So when we're talking about this is going back to just the atomic structure and what it's made up of, right? So we have 3 main things that we're going to be talking about. We're going to be talking about protons, neutrons, and electrons, and how they all relate to each other. Okay, so before we jump right in, let's just go over formulas that we should know and different notations that we should definitely have memorized. So on the periodic table, what you're going to find, and there's 2 different types of kind of looks here. So this is just isotope notation. Remember what an isotope is really talking about is it's just different versions of the same element. And what's essentially changing is the amount of neutrons or really the atomic mass. That's what is going to be changing, or the mass number is actually going to be changing when we're talking about an isotope. It doesn't mean that our protons or our electrons are changing. Those are staying the same. Only thing that's changing are the neutrons and the mass. So this is what it's going to look like when it's in its isotope notation, where on top A is going to be our mass number, and then on the bottom is going to be our atomic number. So don't get those mixed up. I know, why did they choose A to be mass number rather than atomic number? But that's just how it was made to be. So just make sure that you know for isotope notation, on the top is the mass, on the bottom here is going to be the atomic number. And then it's different on the periodic table. We'll see it's switched, right? Where we're going to have the actual atomic number on top, and then the overall mass, atomic mass of that is going to be on the bottom. But that's not the same as our mass number. Okay, so something else to know. Something else to know is just our atomic number is going to be the exact same. It's actually telling us how many protons and how many electrons there are with that element. And then, of course, when we're talking about protons and electrons, we're talking about something that is neutral, meaning there is no charge or really no ion. So we're not talking about ions in this case. We're just looking at a neutral element. And then next, know that your mass number is going to be equal to the sum of your protons and your neutrons. We were talking about products so much. So of your protons and your neutrons, right? So I'm going to apply this now. And let's say we were given carbon 13. Another way to write this, in the case that you see it this way instead, this is in isotope notation. So what you would do, let's say if you're just given the first part, this little dash and this value is actually telling us the mass number. So this is the new mass number, and that's what it's hinting that this is actually an isotope, because if we were to look at the periodic table, the overall mass that it typically has is 12.01, or roughly 12. So I know that this must be an isotope because it has a different mass. So, okay, then I also would have seen that on the periodic table, what's our atomic number? Well, our atomic number is 6. And I know that must mean that, okay, that's going to tell us our electrons and our proton count. But what if they gave us a different form, if they gave us isotope notation? And remembering that isotope notation is actually giving us the mass number on top, right, the 13, and the atomic number on the bottom, which is 6. And of course, it's telling us what type of element this is. So what I can do is the whole point of this, by the way, is to actually draw out the overall diagram or orbitals to understand how this is actually going to look like. So what I'm going to do is I'm going to figure out what my proton amount are, how many protons I have, how many electrons, and how many neutrons, to then draw everything out. So on the periodic table, this is what we said, right? This is what we can compare and see how it's a little bit different. So I know my atomic number is 6. So that means my protons are 6 and my electrons are 6. Next, what I'm going to do is I'm going to figure out how many neutrons we have. So I'll plug everything in. We know the mass number is 13. We know the protons are 6, and we are trying to figure out what our neutrons are. So all I have to do is subtract 6 to both sides, and then that's going to give me 7. So we have 7 neutrons. So now with all this information, let's draw this out. So drawing this out, this is kind of just your standard typical drawing. And essentially for Bohr's model, we just want to see how many protons and neutrons are going to be in the center, because that's talking about our nucleus. And then on the outside, we're going to have our electrons surrounding it. But it is going to be important to know where all the electrons are, how many electrons we have, and how many we have in the inner shell and on the outer shell. And by shell, I'm talking about these rings, all right? Inner and then outer. So remembering valence electrons is going to be very important here, because valence electrons, remember, are talking about the electrons on the outermost shell. So if I know the valence electrons of carbon, I then know how many electrons are on the outermost shell. And then from there, I can then figure out, well, how many are then left to then put in the inner shell, and those would be called our core electrons. Those are just the ones closest to the nucleus. So let's go back to, and then by the way, I would put how many protons and neutrons I have, right? That's what I found here previously. Let's go back to valence electrons. And this is definitely something you need to have memorized, how many valence electrons there are for all of these that are shown on the screen. So if we're looking at carbon, how many valence electrons do we have? Well, we have 4. So I know, okay, 4 valence electrons. That's going to help me out. So what I'm going to do is I'm actually going to place 4 valence electrons on the outermost shell. And those are going to be our valence electrons. So since we have a total of 6 electrons, and I already placed 4, I'm missing 2. So that means I only need 2 on the inside. And that would be our overall structure or our diagram. We'll do one more. So now let's do this with oxygen. So once again, it could either be in either or of these forms. We could either see that this is just oxygen dash, and it gives us our different mass. So this tells us it is an isotope because oxygen's typical mass on the periodic table, or typical mass in general, is 16, right? So because this is 18, I know this has to be an isotope. Another thing is if they actually provided this in isotope notation. So then I know, okay, well, this is in isotope notation. What else is this telling me? Well, I know the mass number. I know the atomic number. And I can go from there. And this is just what it looks like on the periodic table. So I know that our atomic number must be 8, protons are 8, electrons are also 8. And from there, I can figure out my mass number. So plug in how many protons we have, which is 8. And then we figure out how many neutrons do we have. Well, I'm going to subtract 8 to either side. And then we have 10, right? So we have 10 neutrons. Now that we have this, we can build this diagram. So from here, I'm just going to place how many protons and neutrons we have in the center. And then next, we'll go back to how many valence electrons we have for oxygen. Well, for oxygen, oxygen's right here, we have 6 valence electrons. So we have 6 valence electrons, so that means 6 will go on the outermost shell. And then how many do we have remaining? Well, if we have a total of 8 electrons and there's 6 valence electrons, I need 2 more in the center. So, okay, in the inner shell, I will have 2 valence electrons, and that's exactly what you would do. Just knowing your valence electrons is going to help you so much, because then it just becomes a lot easier of just putting your valence electrons on the outside and then working your way in. So that was everything. I know that we went through a lot throughout this time. Now, guys, if you have any other questions, if you didn't get your questions answered, or if you would like to, then what I recommend you guys do is tweet me. So make sure to tweet me at @HelloMelissaM and use the hashtag AskMelissaMaribel live, and then actually Ask Melissa Maribel. And then from there, what I want you guys to also do is either take a picture of your chemistry question or just let me know what topic isn't making sense. I do highly recommend, if you want a specific question or me to cover something specifically, make sure to take an actual picture of your chemistry question and you can tweet me that. To also make sure that I can get the question ahead of time, do that throughout the week. So the earlier in the week, the better, because I write my lessons on Saturdays. So Friday at the latest is when I decide what questions I'm going to pick and answer. So make sure to do that. And then also, if you have questions right now and if you need additional help, I always have resources in the description box. So besides all the different notes or all the different formula sheets that I was talking about, the survival guide, that's going to be in the description box right now. And towards the bottom, you're also going to find other resources that I recommend. So I used Chegg Study when I was in college, pretty much throughout my entire duration of college. It was a lifesaver. It was really helpful because it helped me understand what my homework was saying. So I know a lot of times when you look at a homework question and there's a lot of parts to it, or sometimes it just looks like a foreign language. So it was just nice. It kind of served as like a translator to understand all the different steps or anything that I was missing or not understanding. Chegg Study was a way to just understand my homework, and it was a lot more affordable than hiring a tutor. So I definitely recommend you guys check that out. The links will be in the description box towards the bottom. Okay, so next time it will be live. All right. So if you guys want to join me on the next live, it will be next Sunday and at 12 p.m. Pacific time. So make sure to look out for that, and hopefully it will be up and running and working next time. But at least we can be here. So thank you for joining me, and tweet me throughout the week, and I'll see you next Sunday. See you guys.